I'm Rajeev Thakur, by the way. I also work at Argonne and I've been working on MPI for a long time. So all of you have used, everyone who has used MPI has used data types, although you may not know it. But you probably use the simplest of the data types, what are known as basic or intrinsic data types in MPI. So every MPI function, whether it's for communication or I/O, it takes a buff count and data type argument, and sometimes more than that, because you could specify the data type at the target also in the one-sided communication. So that data type describes how is the data laid out in the buffer that you're sending. And typically, you would, in most programs, you would just have that data type as the basic data type in the program. So if you're sending floating point numbers, you'd call it MPI float, or if it's integer, it'll be MPI int in C. But the data type, the concept of data types is quite powerful in MPI because it allows you to create what are known as derived data types, which can describe any arbitrary memory layout, typically a non-contiguous memory layout, and send that with a single MPI function. And so for example, if you had a buffer in memory and you wanted to send only the green and the blue parts of that buffer, which is non-contiguous, there is a way to describe this layout using contiguous and vector and other kinds of data type constructors, which we will see, and send it with a single function. So the advantage is that you don't have to do the memory copying into a temporary buffer because that is inefficient. It also takes up more memory. You can let the MPI implementation do it in an efficient way. And we'll see how that is done. So as I said, there are two types of data types, the basic data types, which are used to build these derived data types. Why do we have these basic data types in the first place? If you do just socket programming or the POSIX file I/O, there is no data type. You send the number of bytes. So you do size of int times the number of ints, and that many, that's the amount of data you send. In MPI, that is discouraged. You could do it because there is an MPI byte type also. And so you could do the usual size of something and pass MPI byte as the data type, but that is discouraged. One of the reasons is that if you were running on a heterogeneous system, and by heterogeneous I mean different byte ordering. So if you're running on a cluster that had some Intel chips and some other chip that had different byte ordering, if you just used MPI byte, and you had an MPI implementation that could run across such a heterogeneous system, if you just used MPI byte as the type, you would have to do the data the reordering yourself to get the right data. Whereas if you pass the right type, so you said that your buffer had MPI had an integer type or a double precision or whatever, the MPI implementation could do the reordering for you, and you get the right data in the right buffer. So that's one reason to do that, and you don't need to do the size of business. MPI 2.2 added some of the missing types so originally MPI did not have all the language types defined. It had the most common ones, but now pretty much everything that is defined as a basic type in C can be expressed as an MPI type, including the int64 and the int32 and those kinds of specific sized integers and so forth. Okay, let's look at how do you create derived data types out of basic data types. So the first, you call data type creator or constructor functions to do that. The simplest among them, so we'll look at several of them which are increasingly complex. They're not very complicated, but this is in order of complexity, and it's also in order of decreasing performance. So we'll see that. So the first one is MPI type contiguous, which is easy. What it does is, if you want to create a contiguous data type, which means there is no stride or no gap between the individual data elements, you can call MPI type contiguous, where count is the number of items of the old type that you want to describe, and what it returns is the new data type, which is effectively a contiguous type. So what this function and other constructor functions do, they don't really do anything as such for you. You are describing the memory layout that you will use in a future communication or I/O or whatever. And after calling this function, you also need to do an MPI type commit, which I will talk about a little later. So in a real program, you would do type MPI constructors and then call MPI commit, and then you get a data type that you can use in an MPI send. Now, this function, although it exists, is not so useful in the sense that you don't really need to use it. So, for example, if you are you mostly don't need to use it. There is a use for it. If you just want to send this data, you don't need to create a contiguous data type and then send it, because when you do a buff count data type, you can simply send the count equal to this number, and that by definition is defined to send a contiguous amount of data starting from the first to the end. So if contiguous is the last type in your data type construction operation, you don't need to do it, because the count operator in the count parameter in the MPI functions does that for you. Where it is useful is if it is used to build more complicated types. So if you have a very complicated memory layout where there is somewhere in between where it's a contiguous of something that you need to pass to something else to make it a struct or something, that's where it is more useful. So one thing you could do in your code is to see whether if there is a MPI type contiguous anywhere, probably you could remove it. It may not be needed. It may not do much harm either if it's there, because it's easy to implement and the MPI implementation can easily optimize it. So if it's there, it's probably not doing any harm performance-wise either. Okay, so that was contiguous. The next one in the list of types is a vector type, where and the vector means you have a constant or uniform stride between these blocks of data that you need to send. So for example, if you want to send something like this, which has a nice stride of 3 elements between the blocks that you want to send, and each of these blocks is of size 2 elements. So this can be expressed as a vector type. So the way you construct it is you call MPI type vector. Count is the number of these blocks in the vector type. The block length is the number of elements in each block, and the stride is defined as the gap between the first item in the second block and the first item in the first block. And this is, in a vector type, that's the same one that gets replicated. And then you pass your old type, which could be MPI int, if this is an integer array. And what you get back is a new type, which is a vector data type, which just represents this kind of layout. And you can do something, you can use it in more complicated ways itself. Let's say instead of an integer, your basic element, what you want to send is something more complicated, where the basic element itself is we'll look at a struct type later, but it has a different, it might have some other type here followed by a gap and 2 other things, and these are in a strided form. You can do that as well, because all these data type constructors can be recursively called. It's not just that you start with the basic type and you get a derived data type. You can feed that to another derived data type constructor. So you can pretty much describe any layout in memory that way. Is this clear? This is one of the easier ones. The next one is of course, what if your stride is not uniform? You have more of a oh wait, there is one more in middle. There is a vector type and there is an H vector type. So the difference between the two is this how you describe the stride. So in the vector type, the stride is in terms of the number of basic data types. So here the stride would be 3, regardless of what the basic data type is. So if it is a double precision, the stride would still be 3. If it's an int, it's still 3 because it's in units of that old type. If you want to specify the stride in terms of, yeah?
Sorry, can you go back to, yeah. So here, what you want to say in the second case is only the green parts, right?
No. In the second case, you want to send the blue and the green as well. But the blue might be a different type. So you've created a struct type here. And there is also a gap here. So this is a more complicated type that you've created. And the struct is something we see 3-4 slides later. But this is like a vector because these are blocks of structs. And let's say this is a uniform stride because this thing continues. So you want to send this blue and the green all together without the white stuff. Yeah, so what I was saying was that the stride is in terms of, is a count of the number of basic, number of old types over here. If you want to specify the stride as, in terms of bytes, then you use the MPI type create H vector, where the stride is of type MPI A int. So does everyone know what is an MPI A int? If you've used MPI, you probably had to use MPI A int somewhere. So MPI A int is an address-sized integer. So it is an integer that is big enough to represent any address in your MPI program. So typically, it's a 64-bit integer these days. In the past, it could be either 32 or 64, but now it's hard to find 32-bit address spaces. So, but that's decided by your MPI implementation. So wherever you're running, the MPI implementation will define MPI A int correctly so that any address can be represented. And since you are in this H vector, the stride is in terms of bytes, not in terms of the size of the old type. You need an address size integer. That's the only difference. So those are the vector types. Now, if you don't have a uniform stride, you can create an indexed data type. So the difference here is instead of a nice uniform stride, there are these gaps that are unequal. So the only way to represent them is an array of displacements. So this, the difference between the vector and the indexed is that instead of that uniform stride, you now pass, you have to fill in and pass this array, giving the displacements of each of these blocks. So now there are two arrays. There is an array of block lengths also, because each of these blocks could have different block sizes. So MPI is designed so that you can represent any pattern. So that's why this generality is also there: array of block lengths and the array of displacements, and you pass the old type and you get the new type. Is this clear? So for example, if you wanted to pass this is how you would fill in those arrays. The block length array would be, this is of size 1, 1, 2, 1, 2, 1. So that's your block length array. And your displacement array would be, this is at displacement 0, this is at displacement 3, this is at 5, this is at 9, and so forth. So it's simple. You are describing what you want to send. So that was indexed. So in MPI, this has been there since MPI 1 days, and at that time, from that time, these block lengths always had to be passed as an array of block lengths, assuming that they would be different. So if they were the same, say, suppose all of these were blocks of size 2, you would still need to create an array and then fill all of it with 2, and pass that. So that is, first of all, it consumes some memory. Suppose this was a very big layout, then you'd be wasting memory, and it's kind of inconvenient that to have to fill in an array with the same things. So sometime later, I believe in MPI 2.2, a new function was added to fix that problem. So instead of an array of block lengths, this one type create indexed block takes a fixed block length. So all of these are 2, and then you just pass block length of 2, and the displacements are, of course, and it's an index type, so you do need a displacements array. So this again shows that MPI is not a small, that's why the standard is 800 pages or whatever. It doesn't have a limited set of functions. Whatever you need, you might find a separate function just for that. So it's meant to be used by library writers or advanced programmers who want what they need. It doesn't add overhead to the implementation to have these many functions because one function doesn't affect the performance of the other. It provides some convenience. MPI could have provided just one function, the most general type of data type, and you use that for everything. But that's not convenient. That's not a good style. So this is the type create indexed block. So we have looked at vector H vector, the difference being just the size of the stride is in bytes or in number of elements. And then the general version of that is indexed. And the default indexed takes an array of block lengths. So there's a new one that takes a fixed block length. So the next one will be the H indexed again. So this is the same difference as vector H vector. Here the displacements are in bytes, not in terms of count, number of old type. So it's a similar concept. And there is also a type create H index block that was missing and added now in MPI 3, I believe, but I don't have it listed here. And the most general type is an MPI is a struct type where so far we have had you could have varied block lengths and you could have varied displacements, but the old type is still the same. So all of these are integers or all of these are double precision or whatever. What if even your data type, the basic type itself was different? So for that, you can use the struct type where even the MPI data type itself is an array of types. So let's say you had a struct in C which had different fields in it and different types. You could have a int, you could have a float, you could have a character array in there. How do you represent that in MPI? You can use an MPI type create struct because you can pass different old types in that, and of course you pass the right, you fill in the other fields appropriately to represent that struct data structure, and you can send that as well. Okay, and there are some convenience functions provided. So actually, just these the vector index struct. These are sufficient to build anything you want. It can get a bit complicated though, that is you might need to think about exactly how to use them. So a couple of convenience data type constructors were added. This was done in MPI 2. It was done originally to support the MPI IO, the MPI file IO functionality, because this is really needed there. In MPI IO, you could be reading a large 2D or 3D array from a file, but you're not reading the whole array. You're sort of dividing it, distributing it among the processes. So you want a subarray or a small piece of that array. How do you get that efficiently? How do you create the data type representing a subarray of an array? That it gets a little tedious if you're doing a 3D array or a 4D array. To build that data type out of vector and struct or whatever is a little tedious, and you can make a mistake in doing that. So this is a convenience function where you can, let's say you want some this can be for any number of dimensions, some subarray of a bigger array. You can describe that in terms of array notations. So this takes the number of dimensions of the array, the size of the global size of the array in each dimension. So by array of sizes means it's a list, but it's the global sizes in each dimension. Then the size of the subarray in each dimension. So you pass this size, the size of this and the size of this. The array of starts is the starting index, the starting indices of the subarray in each dimension again. The order is whether it's a C order or Fortran order, whether it is row major or column major. That you have to specify that, and then you pass the old type, and what you get out of it is a new type describing this layout. So this is a non-contiguous layout. These two are, if it's a C array, then these two are contiguous, and then there's a gap, and then these two are contiguous. And it gets more complicated if you have more dimensions. And if it's a Fortran array, it goes column, major, and so forth. So if you try to build it yourself, it can get difficult. So you can use the subarray type. There is another array data type constructor called a distributed array constructor, which is a little simple, but it can also be a little tricky to use because it assumes a very specific distribution of an array. So in those days, when MPI2 was defined, there was another language called High Performance Fortran, HPF, which has sort of disappeared now, which was an extension to Fortran where you could declare a distribution for your array and then just write your program without any message passing in it. The compiler would generate the code to do the message passing. So it had a definition for data distribution. There was a block cyclic and block cyclic. So this assumes that definition, and you specify whether it's a block distributed or a cyclic or block cyclic, and this constructor creates the derived data type for you. The risk in using it is that if the data distribution in your program doesn't exactly match the distribution as defined in HPF or what this uses, then you'll get some wrong results. So you have to be careful, and that happens when some array size in some dimension is not evenly distributed, evenly divisible by the number of processes. So if you have something is of size 100 and you're dividing it among 12 processes, then it's an uneven distribution. Who gets the uneven? So HPF has defined that to be a C, and it's a ceiling division of that size, and then whatever is left over, they get the remaining pieces. If you follow that notation, it'll work. If you follow some other convention, then you'll get an error. So we discourage the use of this unless you need to. So those are the main constructors, but it's general enough and flexible enough that you can define anything. Then there are a few other things that you might need when you're using this. So if you're using say an MPI struct type and you're using the absolute memory address of a buffer in your data type, then when you're doing an MPI send, your buffer address, the address that you pass to buff count data type, you have to pass that as MPI bottom, which really means it's the starting address in your address space. Think of it as address 0, for example. So that's just detail. If you need to know it, need to use it, it's available. Then there's a function called MPI get address to know the address of a variable portably in different languages, which you might need in some data type constructors and so forth. Then, as I said, this is important that data types, before you use them, you have to call MPI commit, MPI type commit. So the way it works is you call your data type constructor function, and if that's the last one, that is, if you've got your data type and you want to use it, you have to call something called MPI type commit. If you're using that data type as input to another data type constructor, then you don't need to call commit. You can just directly feed it. The idea here is when you are doing this data type construction at the very end, by calling commit, you're telling MPI that I'm done with my data type construction, because it can get complex. But now you can try to analyze what I have done and save that in some way internally, so that when I do communication repeatedly with this derived data type, you know what to do. You have understood the data layout. You can save the time that you would spend trying to figure out, is this a vector type? What is the stride? Or how complex is this? How should I implement it? Should I do a should I allocate memory and just copy it contiguously and send it? Or can I send it in a strided way? All that, the MPI implementation can decide at MPI type commit. And in the actual sends and receives, it can be done. The communication can happen more efficiently. So that is required. If you don't do it, you'll get an error in your program saying you're passing an uncommitted type to the communication function. And similarly, you can free the type once you're done with that. You can also duplicate a type. That is, you create and this is similar to an MPI com dupe. You can duplicate communicators. So that just creates another copy of the same data type, and it's used more by libraries. So if you're using some third-party library, they want to maintain a copy of what you've passed them, so that if you free that type, they are not in trouble. That is, they still have something to use. So that functionality also exists. There are other functions. So there is functionality in MPI to actually so pack. There's an MPI pack function and an unpack function. So given a non-contiguous data layout, there is a way to pack it into a contiguous layout. So that's quite different from the derived data types, where we say that you should not do that. But this was there mainly because in those days when MPI-1 was first defined, there were other libraries, PVM and others, that had this functionality. So there were codes that sort of were used to doing that kind of thing and needed that function. So it exists more for historical reasons. Then there are other sets of other functions that are more useful to libraries. And the idea here is, suppose you're passed an MPI data type. How do you know what that represents? So the user has created a fancy derived data type and passed it to the library. The library may not understand what that is for. Or, for example, an I/O library wants to do I/O, and the user has passed his derived data type describing some file layout. How do I know what that represents? So there are two functions, MPI type get envelope and MPI type get contents, that allow you to sort of unwrap or figure out what that data type is about. So it's effectively the opposite of constructing the data type. It deconstructs the data type in a particular way and tells you how the data type was constructed. So it's more useful for library writers than application writers. And there are more advanced uses of where you can change the size of a data type, and you can change what is known as the extent of a data type. The extent is basically, there is a way to create data types that have a hole at the end, a gap at the end. So that gap is, the extent includes that gap, the size does not include that gap. It's a lot of detail, and if you're interested in any of that, there's a mathematical definition of what is the size and what is the extent of a data type in the MPI standard. And before playing with that stuff, it's good to know exactly what that means, because you could make a mistake and then the code will do the wrong thing. You'll get wrong results in that part. Okay. So in terms of complexity or what the implementation can optimize, clearly, if you are closer to the left side, that is, your data types are contiguous or vector or even indexed, indexed with a fixed block size, those are easier to optimize or easier for the MPI implementation to even understand. As you get further to the right, or if you have built very complex types, sometimes the MPI implementation might just say, okay, this is too complex for me to optimize. I'm just going to internally do packing and just copy it together and then send it as a contiguous. Of course, that's an implementation choice. And there's a lot of research in how to optimize MPI-derived data types, and there have been papers published on that. So it can vary based on the implementation and where you're running and so forth. But in general, we encourage you to use data types, and if the implementation doesn't well, you can always complain to the vendor of the machine or to the MPI implementers, including us, and that's how you can get better performance, because historically, derived data types have not performed well, so users have not used them, and it became a chicken and egg problem because no one was using them, no one bothered to spend time on optimizing them. But things are changing, and they have changed, and so we do encourage you to use these functions. Okay, so I think that was all in the area of, yeah.
So in this hierarchy where things to the left on that list are generally preferable to things to the right,
Yeah.
would something like a vector of structs be a reasonable data type, or would that slow you down because you do have that struct data type built in?
So it depends on the complexity of that struct, I think. So if it's just a simple struct, it might be okay. But again, if that struct has been constructed out of something else, something else has been fed into creating the struct, it might get difficult. In general, struct, at least some implementations, when they see a struct, they might, and particularly if the struct is not contiguous, there are gaps in that struct, it might say, okay, I'm just going to do the general copy or something there. But the easiest would be a vector of basic types. That is easiest to handle. Even indexed can be easily handled, I think. Yeah?
If I have a struct of, say, 4 doubles, just 4 doubles,
Yeah.
and then I have a vector of, say, 10 of these structs,
Yeah.
better to use a 10 of structs or?
No, but if you're just using 4 doubles, don't use structs. So struct is useful when you have a mix of data types in your. So if you have only doubles, then so you can just do a vector type then, because yeah, you have some number of doubles and then a gap and some other doubles, you're saying, right? So part of what this is saying is don't use a complicated type if you don't need to. The struct type is general, and you could use it for anything by just passing in nulls or whatever. But then the implementation might give up saying that, oh, it's a struct. So in your case, it sounds like it's just a vector type, probably, right? There's only
It's a vector of 4 doubles,
repeated.
repeated.
Yeah, there's a gap in there, right?
There is no gap. There is just 4 doubles, then again 4 doubles.
Oh, then you don't need data types at all. You can just do MPI send and 4 time, it's a contiguous buffer, right?
Correct, it's a continuous.
Yeah, so don't use any of this at all then, because that's what this also says that, yeah.
Is it better to use struct of vectors or vector of struct?
It's not a question of better. It's what can represent your pattern. So if your pattern can be represented, you should go in this direction. And what is the first thing that can represent your pattern? And then use that, because that is the easiest to do.
Yeah, I would say the answer to that question is more controlled by memory locality issues on your core, whether you pick that. And it's, for some things, the array of structs of arrays is even best. So you optimize for your local core, then the MPI data types give you a way to describe whatever you ended up with. And a very good implementation would be able to figure out how best to move that.
Is there any case, for example, some choice is good for my local core, but actually for MPI, the other choice would be better? Is this like that?
Yeah, no, that happens. It depends. It really depends on where the most memory access is, where you end up taking the less efficient choice. And so, in many cases, it will be the computational access. The access is doing the computing. So whatever is best for the core is probably the best. For MPI, what normally happens is the data is marshaled into some location and then sent. The question is whether the user does that, in which case it might be then copied again, or whether it's done inside the MPI implementation. Again, some implementations aren't very good at that, so the cost of that can be high. There are implementations, there's certainly an example implementation that we're putting into MPICH right now that does just-in-time compilation for the data type moves. So that's the way it should be done, nice and fast. So even if that's slower per byte than what you use in the computing part, that computing part is probably dominant. So I would optimize for what you need to the core.
Yeah.
So what's the cost of subarray compared to struct with 2000?
Oh, yeah. So subarray is just a convenience type. So it is it is somewhere in this range. It might internally use a struct for something, but it's more of an indexed type.